Hello, I'm Ilias Cholis, and I'm going to talk to you about how we can use cosmic ray lepton measurements to probe the properties of Milky Way pulsars. This is work in collaboration with two talented undergraduate students, Tess Hoover from Oakland University and Iason Chromidas from the National Technical University of Athens in Greece. Now, pulsars are rapidly rotating, highly magnetized neutron stars. And we want to study them as sources in terms of their high energy cosmic ray output. This is an example of one of the youngest pulsars in the Milky Way, Crab, which is about 1,000 years old, and this is its observations in radio, optical, and X-rays. So through observations like those and gamma rays that I don't show, we understand that pulsars are environments that are very rich in terms of cosmic ray electrons and positrons. Now, pulsars, we also understand that they lose their spinning energy into electromagnetic radiation and in cosmic rays. The power by which they lose their energy is known as spin-down power, and it evolves with time, and it can be modeled through such an equation where tau zero is the characteristic time scale of loss of energy. E0 is the origin, E0 dot is the original spin-down power, and kappa is called the breaking index. The value of kappa of 3 is the equivalent of a rapidly rotating magnet around an axis that is on an angle with respect to its magnetic axis. From this equation, you can understand that if given enough time, much larger than tau zero, the total energy released from a single pulsar is basically going to be its original rotational kinetic energy. So how do we model pulsars as cosmic rays? I'm going to use 3 units in this talk: years or kilo years, mega years. Parsec, 1 parsec is a little more than 3 light years, and GeV for energy, or GeV is a billion electron volts. So it turns out that pulsars have a typical spin-down power time scale of about 10 kilo years, which is much smaller than the time it takes for the cosmic rays that are produced from a pulsar that is hundreds of parsecs away from us to get to us. And that means that pulsars are effectively time bombs of cosmic rays. So what would be the effect of that in terms of an observer? This is energy on the x-axis, and on the y-axis is basically the flux of these cosmic ray particles multiplied by appropriate power of energy to make the figure easier to read. And imagine now you're an observer that will live for more than 10 million years, and on the day of your birth, a pulsar was born with you. So at the time you would be about 3,000 years old, you would observe the first flux of cosmic rays from that pulsar, that single pulsar, and you would observe it only at the very high energies, because those are the fastest moving energies. Then as time progresses, you would see an ever increasing flux of cosmic rays, but at the same time, you would notice that the highest energy cosmic rays you observe from that pulsar gradually drops. After a certain point, even the actual flux drops, while the maximal energy of cosmic rays you observe continues to decrease. Now, of course, we are not observers that live 10 million years. We make observations only for a few years, but at the same time, we don't have just one pulsar, we have many, many pulsars. So this is, in same units as I showed before, the cosmic ray positron spectrum measured by the alpha magnetic spectrometer. These are the data points. The black line is from a simulation. That simulation contains thousands of pulsars. I have highlighted the contribution of only about a dozen of them. And I've actually multiplied their fluxes by some factors to make them be more well within that figure. So a very young pulsar would contribute at very high energies. Relatively young and powerful pulsars would contribute at the end of the spectrum. And while older and more distant pulsars would contribute at lower energies, but would have more prominent peaks. And there are many more of them, though. The observations we use are not just from the alpha magnetic spectrometer, but also from CALET, another experiment on board the International Space Station, and also another satellite experiment called DAMPE. And while pulsars are not the only source of cosmic ray electrons and positrons, and we do include the other known ones, by adding the contribution, we can test different hypotheses on the properties of pulsars. Another observation we use is the cosmic ray positron fraction, where this is the cosmic ray positron flux over the positron plus electron flux versus energy. This positron fraction goes up, and one thing you will notice is this is the measurement, the data points is the measurement, and the lines are theoretical models. You notice that all those theoretical models predict bumps and wiggles. Now, in our simulation, basically, we test many simulations to probe for the fact that neutron stars are born in a relatively random manner with a given rate. Their exact location in space is follow some distribution and some probabilities, but it's still stochastic. We have to include also the initial conditions of neutron stars, which affects what is their initial speed down power, and that has some uncertainties that we have to account for. There are uncertainties in terms of the time evolution of the power from pulses, which is the kappa and the tau zero. We have to include also the fact that cosmic ray electrons and positrons, the cosmic ray electrons and positrons they produce, they come with a spectrum, and they come with an amplitude of that power being converted into electrons and positrons. And also we have to include the fact that once electrons and positrons are produced and injected into the interstellar medium, they have to propagate through it and also through the solar magnetic field. And to account for all this combination of uncertainties and choices, we have produced over 7,000 unique Milky Way pulsar simulations, where each one of those simulations contains anywhere between 5,000 to 18,000 unique pulsars, all of which are within a 4 kiloparsec from the location of the sun. We also use the total lepton flux. This is the measurement from AMS. You can see also the prediction for the individual electron flux, the total electron flux and the total positron flux, and also individual contributions from pulses. So what we do is we basically test all these hypotheses to the data and ask ourselves what works and what doesn't. As I told you, a value of this is look at the columns. A value of k equals 3 refers, as I said, to the example of the rotating magnet. A value larger than k equals 3, which is what is preferred here, this refers to percentages of survival, of what actually gets through the data, is a case where the pulsars slow down, but in a manner that is slower than the prediction of k equals 3. So in some sense, we think that pulsars, as they are time evolving, their breaking index also changes in a manner that allows them to retain more of their rotational energy. Our next goal is to use the fact that pulsars predict many features in the various cosmic ray spectra and search for those features. One way we can search for those features is known as performing a power spectrum calculation, where you're basically trying to see how much power exists in small scales of that actual measurement. And these are my conclusion and what comes next. So after performing all the simulation and using the cosmic rays to basically test the properties of pulsars at ages where the electromagnetic observations are not so sensitive to provide us much more information in terms of their evolution, we have found a clear evidence for a breaking index of larger or equal than 3. We find that pulsars are quite uniform in terms of their properties as sources of cosmic ray electrons and positrons, both in terms of the spectrum they produce and in terms of the fraction of energy that goes into electrons and positrons. We also find actually a feature around 12 GeV in the actual positron spectra, which may suggest an additional subpopulation of sources probably further out than 4 kiloparsec. And we are also in the early stages of performing a power spectral calculations and also a cross correlation between the individual, between the electron and the positron spectra, meaning we are looking for features on both spectra that coincide in energy. Thank you.